Great. Thank you very much. Sorry about that. I'm going to introduce the research we have been doing since I started in the University of British Columbia, and I'm continuing in the Canadian Forest Service on the analysis of time series of remote sensing data, especially Landsat, for mapping and characterizing disturbances across all Canadian forest systems. And I will end by focusing on the non-stand replacing disturbances and the analysis we have conducted around that. So first, I would like just to mention the motivation that we have in our research. Like countries have to fulfill national and international reporting obligations. They are part of treaties and conventions, and they need to keep national forest inventories and carbon accounting programs. So these programs require data for science, data for monitoring the forest, for policymakers, and for management. The issue here is that the required information is not always available, or if it's available, it doesn't have the spatial resolution, or it doesn't cover the whole country, has been acquired at one time, or the categories and the information that is contained in this information is not compatible with the needs. Also, we believe that it's important that the nations and the international programs, they can stand behind the data that they produce. They produce this data using scientific methods, and the data has high quality. If you are going to report about fires, you need to have a good data about fires to stand behind your numbers. And finally, there is a focus on linking the information needs with the data and the organization capacities. So we are focused on the science and the production of the outcomes, on creating these outcomes, but not the infrastructure to make this operational. So we call this prototyping at scale. We conduct our analysis on the whole country. So here I'm listing some of the information keys, information needs that are key for Canada's forest inventory or for the carbon accounting programs. There are two kinds of attributes, basic attributes that are related to land cover and forest structure, and they include elements like crown closure, the age, the species, high volume biomass, and then there is a series of information related with the disturbances that is needed, like the land cover before the disturbance, the land cover after the disturbance, what kind of disturbance we had, when the disturbance happened, like how much this disturbance affected, and what was the intensity of the disturbance. So with this in mind, what is what we are trying to do? So simply, we are trying to map Canada's forest. We are trying to map all the different phases of Canada forest. But not only mapping, we are also trying to monitor. Like if you make a map one time, you have information one time. If you have several maps, you can actually monitor how the forest is evolving and the changes and how these changes are evolving. So if you have 2 days, you can detect changes. If you have 3 or more days, you can actually see trends in the forest. We are trying to, or we use actually science-supported methods. We assess our methodologies. We produce statistical validation, and we make these methods repeatable, so you can monitor, you can produce maps through time, and cost-effective. So the value on applying these methods is also economical. We produce information at a level of detail that includes spatial, temporal, and categorical, that is informative for not only science, but also management and policy developers. And for doing this, we base on satellite data. So the space agencies like NASA or USGS, they have the Landsat, or the European Commission have Sentinels, which are like amazing sensors to monitor the forest. They are sensors that they have a rigorous calibration. and they offer the data for free. So we don't have to pay for taking all this data. These programs are fully operational, and they have been funded for, well, Landsat for 4 decades. Sentinels is almost 10 years. And there is perspectives, like we know when the Landsat 9 is going to be launched, hopefully in September of this year. And there are already plans for Landsat 10. One really important thing about this data is that they offer the data in an analysis-ready format, which limits a lot the amount of pre-processing that we have to do with the data. We can take this data directly and use it in our process. And these data sets, Landsat 30 meters, Sentinels 20, they have resolutions that are informative for analyzing the human interaction with the Earth. So what we did is we took all the Landsat images available for Canada, and we processed them, more than 100,000 images, and we created these composites. We use pixel compositing techniques that choose the best pixels for every single year, and created these seamless Landsat composites of Canada. This series goes until 2016. We work already until 2019. We are going to work soon with 2020. So to create these composites, I mean, in the era of Google Maps, these images might not be too impressive, but we need to think that every single pixel of this image has 30 meters, and every single pixel contains surface reflectance information, which is a physical value that you can link with the quality and the condition of the vegetation. So to create this mosaic, we had to process more than 600 terabytes of data. And we could do this because the Landsat information is free. Like in the old times, with a price of $4,000 per scene, this would have cost $400 million in data. So this just wouldn't happen in the past. So using this information, we can actually track every single pixel and analyze how that pixel develops through time, if there is a change, if there is a vegetation regrowth. So the processing goes like this. We access to more than 100,000 images of Landsat that is open, and we took the images from the growing season in Canada, so from July and August. So we to avoid a seasonality effect, we remove undesirable pixels using the information from the cloud mask. We use the information of the water mask. We remove smoke and shadows. I throw here the words big data and artificial intelligence because we needed to automatize like a lot these processes. We use high processing, like supercomputers, basically, to conduct this process. And this is how it looks like. We created for every single year an image composite. So we have 2004 with some data gaps that are shown in gray. 2005 has most of the information. 2006, we couldn't find like good pixels because of clouds, because of different factors. 2007, we could have again a good image of Canada. So in the first process, you can see in 2004 that there is a fire actually occurring at the time of this image acquisition, and there is some smoke that wasn't detected by the analysis-ready data by the cloud mask. So in the first step, what we did is we analyzed the whole time series to detect those noise observations and flag them as a node data. So we removed that information that were clouds or were smoke, and we created more node data. And in the next step, what we did is we analyze the temporal trends of each pixel. And using the information of the temporal trends, we were able to provide synthetic values in the pixel where there was missing data. So you can see here, I'm going to flick back and forth, with 2004, how all these missing values now they are in field with a proxy surface reflectance value, or 2006, where we went from having almost no data to having already spectral data. Something important that I would like to keep in mind is that as we use in this spectral analysis, we detect the changes at the same time, we are able to avoid transmitting like information from fires and polluting the information in this image. So you look at this image, this fire occurred in 2007. You look at this image in 2006, we don't have spectral information of the fire in the synthetic pixels we are creating. So as I say, we use a time series analysis for each pixel. This represents the time, like the different years of the time series. We use the normalized Bern ratio to detect the change and the changes and the trends. And we feed linear segments. So in case that there is a change, we have no change, we have the change segment, and then we can track the regrowth after that change happened. So the idea is to use this information to extract the changes, to categorize these changes, to get land cover information, and to derive forest structure. So initially, we analyzed every single pixel, and we detected all the changes that happen in Canada, in this case, between 85 and 2015. You can see, like, in the center of Canada, all the land cover changes related with the prairies and the agricultural areas. But in the north, we can see these large fire occurrences. In the south, we can see the smaller changes related with harvesting activity. And if we look at British Columbia, we can even see the effects of the mountain pine beetle infestation in the changes we detect. So these changes cover the whole country, but this information has 30 meters. So this means like we can actually go closer and look at each of the objects that we detected as change. So on the right, I have the date of the detection of change. On the left, there is an animation that is showing the surface reflected composites for each year. So we can see in the northeast some changes related with harvesting activity. In the southern area of the image, we can see some changes detected with related with fire. And in the rest of the image, we can see these salt and pepper objects that are related with the mountain pine beetle infestation. You see around the 2003, 5, 6, 7, 8, you can see a decline in the spectral response on the forest, and we are able to detect these changes. So we can actually analyze each pixel, and we can actually analyze the trends and extract characteristics that describe how these changes are. So we can extract information of the segments before the change, and we can see what was the evolution. We can actually characterize the magnitude, the spectral difference of the pre and post change occurrence, the persistence, how long that change has taken or how long it has taken for this trend to reach the bottom, the rate, so the annual magnitude. We can categorize if it were the first, the last. We can track if there are multiple changes. And also we can actually monitor the post-change magnitude evolution. So we can actually see how the vegetation is recovering after the change, and if the vegetation is recovering after the change. So what does imply? Like this here in this image on the left, I'm showing the change rate in spectral values for each pixel. So this is a normalized burn ratio. So the highest values actually are given for areas that have been burned. We have areas that have been harvested in pink and red colors. And then we can see with the lowest values, spectral values, we can see areas that had mountain pine beetle infestation. So we compare the information that we have on the right, that is just the detection of the change and the year, and the information that we have on the left, that is the magnitude of each of the changes. We can actually start discovering more things. And we can use this information to train a machine learning system to actually classify each of these occurrences in a change type. So this is actually what we did. We, for each object, for each change that we detected, we got characteristics that were geometrical, like the size, the complexity of the shape. We got characteristics of the spectral response before, during, and after the change. And we got characteristics about the whole time series to produce a classification map of the changes. So we use a random forest model, and we categorize every single change as fire, harvest, non-stand replacing. There are also rows that, for a scale reason, are not shown here. And the agricultural information, we use actually an agricultural mask to get rid of those pixels that are really noisy compared with any other forested area. So with this information, it's possible to derive statistics about how the forest is changing annually and overall. So on the left side, I have the area that was burned through the analysis period from the 85 to 2015. And we can see like the incredible variability on the burn area depending on the year. So you have 2 years, like 95 and 89, that actually accounted for the 23% of the area that was burned through all the period analyzed. In total, we got roughly like 50 million of hectares that were affected by fires on the analysis period, which is 1.5 million of hectares per year, with a very high variability, so a standard deviation of 1.1. We compare with the harvesting activity and the area that was affected by harvesting activity. The harvesting standard deviation is 0.1 million of hectares. So the amount harvested every single year is more even. In total, we had about 20 million of hectares harvested in the period with an average of 0.6 million of hectares. So we can see the trend of the harvesting area, how it was increasing through time with a maximum of 0.9 million of hectares in 2005. And then we can actually see the effects of the global financial crisis and how after the 2010, the harvested area level was similar to the area that was harvested in the 80s, at the early 80s. And as I say, we can track the changes, but we can also track the recovery of these changes. So we know that when there is a fire or when there is harvesting, there is a time where the vegetation actually comes back. And if you look at the image, we can see how we detect the changes, but we can actually track how these changes or how these areas that change are being revegetated. So using the temporal analysis of the time series, we can actually track the different stages of the recovery of a forest stand. So we are able to track the disturbance when all the vegetation is gone, but also we can spectrally track the different parts of the forest recovery, like the stand initiation, stem exclusion, the beginning of the understory, and finally when the forest is mature, and maybe in the future there will be some gapping in the forest. So this is all possible to track with the time series analysis. And in fact, we were able to derive metrics from the recovery, like the years to recovery metric, that what it does is it measures the number of years that a time series takes or a pixel takes for the spectral value to be similar to the 80% of the pre-recovery condition. So we can compare actually the recovery after wildfires or the recovery after harvesting activity, how harvesting activity has a much faster recovery, so the years to recover are lower compared to fire. And we can also see differences in the recovery of fires occurred before and after different times to see if there has been a change in the recovery trends of the forest vegetation. Now I would like to move to land cover classification. We are using, we are working with the methodology that we call land cover 2.0, that is opposed to the classic land cover classification of the images that we'll call land cover 1.0. So obviously, in the old times when the land cover 1.0, the traditional land cover classification occurred, like we had limited options. There were not many satellites. There were not that many different resolutions. We couldn't access to all the time series. We had even to pay for some data, which compared with now that we can access actually to a lot of data, and it's mass data processing the requirements that we have these days. Originally, we had to do pre-processing of the images. We had to georeference, calibrate, remove clouds, while now, like sensors and space agencies provide a whole series of analysis-ready data that is already georeferenced, in surface reflectance value. They tell you where the clouds are, they tell you where the water is, where the snow is. So, you know, like the processing load has been reduced a lot. Originally, like the land cover classification was done with simplistic algorithms, like maximum likelihood, that had assumptions about the nature of the data. And currently, like machine learning is used, I would say, mostly, like random forest has become a standard in remote sensing community. But the important thing here is that the land cover classification and the change detection is something that is done like integrate in an integrating fashion. Originally, you will create your land cover classification, you will have your land cover map, and if you were lucky and you had two images, you were able to actually detect the changes and compare where the changes happen. Like with the new approach of this land cover classification, changes and land cover are produced at the same time, or at least are produced in a synergetic way. After the changes, you can, if you do after the land cover is classified, if you have a land cover series, you can reduce the errors. So, you know, like a pixel with water won't have the next year a forest and then go back to water. So those are things that you can correct. And there is an accuracy assessment process that in many cases now is iterative. So you can learn from your errors and go back to your algorithm at some part from the very beginning or from the part of error reduction and improve the quality of your data sets. And finally, like sharing the information now is much easier than it used to be. Like platforms like Google Earth Engine or Esri offer like websites where you can actually make a map and put it up there. So that's much easier to reach everyone with your information. So using this approach, we classified every single year our image composites, and we use the change information to ensure the temporary consistency of the time series of land cover maps. So we use a methodology called hidden Markov models that avoid that unlikely transitions, like the one I mentioned about water, forest, water, occur. So we map every single year all the Canadian forest system. So with this information, we are able actually to monitor and to get statistics about the land cover and the land cover evolution. So here, and this is what I normally refer as the most boring graph I have ever made in my career, is the land cover distribution every single year on the total of the forested ecozones of Canada. So we can see like at this level, like there is almost no variation in the land cover distribution. So the tree classes that are well-done tree, coniferous, broadleaf, and mixed wood are the bottom far the bottom colors in this graph, and we can see like virtually there is no variation on the amount of trees in the distribution of land covers. But we have information on the changes, and we have information on the type of changes. So what we did is actually we went away and we mapped the distribution of the land cover before and after the harvesting events, and we plot them based on the time. So the year 0 is when the change happened, and we, for every single change, we went back and forth for after and before the disturbance. So here I'm representing all the harvesting events that occurred in the from 85 to 2012 in Canada, and we can see obviously like the land cover before a harvesting event is mostly tree areas, and after the harvested event happens, we have an abundance of herbs and shrubs, and as the time since the change happened, we see an increase of different tree types like mixed wood, broadleaf, and then at the end of the time series we can see an increment of coniferous. And we can compare this with the evolution of the land cover before and after fire. So here is the population of pixels that were accounted. You can see like while harvesting is something like the amount of area harvested is quite homogeneous every year. There are not big steps like in the fire that you can have a year with more or less fires. And we can see like 60% of the area that was burned before the fire, they were treed area. And then after the fire, we have exposed land, we have a lot of shrubs or the shrubby vegetation that is that has some like dead trees, remaining trees, and we can see a much slower return of the tree land cover classes in the time series. Also, keep in mind like the variability of this time series at the beginning and at the end of the graph, just because the population is much lower, so there is more noise. So far we have the changes, we have the image composites, and we have the land cover. The next thing we did is we put together LiDAR information from the LiDAR plots with our change information and spectral composites to derive forest structure. So we use the LiDAR transect that was collected in 2010 that covers 25,000 kilometers of Canada boreal forest. And we added also information in British Columbia, information about the hemi-boreal characteristics of the forest. And using an area-based approach, we derive for every single 20 by 20 meter cells, we derive different forest attributes. So we had a series of attributes derived directly from LiDAR, like the mean height, the dominant height, like would be the P95 height. We had the canopy cover, that would be the percentage of points, the return of points above 2 meters. And also we modeled a series of characteristics for like inventory, like forest inventory characteristics from this LiDAR data. So lowest height, basal area, steam volume, and above ground biomass. So using an imputation model, we actually provide for every single pixel that was a tree in Canada, we provide a value of the different forest structure parameters, like canopy cover, canopy height, above ground biomass, load height. In this case, I'm just showing the difference of the trends between the beginning and the end of the time series. But as we have the whole time series and we have that information annually, we can actually go away and see the evolution of each of these pixels and how the biomass is behaving for each pixel. And we can actually analyze the behavior of the biomass in areas that are dominated by fire, areas that are dominated by harvesting activity, or even in areas where non-standard places disturbances happen. So this is what we did. We went away and we got, sorry. So we got the area that was disturbed, the treat area that was disturbed by the different factors, harvest, in blue would be non-standard placing, and in red would be fire, and compare annually for every single year with the above ground biomass losses that are related with all of these disturbance agents. So we can see like overall there is a consistency on the values of area disturbed and above ground biomass loss. Obviously, the years that have the greatest losses correspond with the year that there was an exceptional fire activity. We can see like harvesting, as we said before, the area harvested is quite even through the time, but it is also the area that was affected by non-standard placing disturbances. But if we look at the impact of the harvesting on the above ground biomass, we can see that the harvesting has actually 5 times greater losses, or the above ground biomass lost by harvesting is 5 times bigger than the above ground biomass lost by non-standard places disturbances. Even when the harvesting is only 1.3, the area harvested was only 1.3 bigger than the area affected by non-standard placing disturbances. And I will use this as a link to introduce our research with the non-standard placing disturbances. And I would like to first make these distinctions between change as an event or change as a process. So if we think about a change on a fire, like we think about it as an event. So you use an annual time series of Landsat data as we do. A fire will happen between 1 year and the other. So the duration of that event would be within 1 year. But if we are studying other elements like infestations or water stress, these changes are much slower. They are much subtle, and they take much longer time to occur and to manifest on the forest, and also to be captured by the remote sensing. So remote sensing technology is able to monitor vegetation disturbances, like we know that. And the thing is, like standard placing disturbances like fire and harvesting are likely to be detected with much better accuracy. That is what this graph with the cute worm and the fire is representing. So the accuracy to detect areas that have been burned, that have a big severity, and they have objects with a big extent, the accuracy will be higher than the accuracy that we get on the detection of non-standard placing disturbances. And on the same token, like the confidence intervals on the detection of fire will be smaller than the confidence intervals that we will have on the detection of non-standard placing disturbances. So, as I say, like non-standard placing disturbances are low magnitude and subtle changes on the land cover condition, but they don't produce a removal of the vegetation. So, or like an overall removal of vegetation at the stand level. So the land cover should remain the same. And what we are doing is using our time series, we are analyzing the temporal traits of the non-standard placing disturbances. So we use the pre-disturbance spectral value as information about the productivity of the forest that is affected. we use the persistence of that change, how many years has taken for that trend to reach the bottom, and we also analyze the change magnitude. So our theory is like events like water stress will have a big severity, and they will happen faster than other changes like defoliations that are expected to have a more gradual change and a longer persistence. Or we expect like disturbances like the ones produced by a bark beetle have different trends related to the different stages of the attack, which ultimately will end up in killing some trees of the stand, or fungus, like they will have a fast mortality at the beginning, but then this mortality will be reduced, or this spectral response related to the mortality will be reduced as the stand builds defenses. So what we did is we actually map all the non-standard placement disturbances on the treat areas in Canada, which are shown here in green. And in red, we have the standard placement disturbances as comparison. So overall, our numbers indicate that 0.9 million of hectares are affected annually by non-standard placement disturbances. And those on tree vegetation would be approximately half of those of this area. Now, if we compare these numbers with the ones reported only by insects by Canada's National Forestry database, like they report 16.6 million of hectares affected by insects every single year. So, like, what is happening here is we detect the changes at the pixel level. We detect the small blobs and big blobs that are represented here in blue at the pixel level. And we record the occurrence of the change at the end of the time of this spectral, at the end of this spectral trend. So even when this change has been occurring through this time, we record as a change year the end of the time series. So we could potentially transfer that information through all the years where that change happened. That's one thing. The other thing is like the data sets that are used to map and to monitor the infestations of the water stress. They are made using aerial overview surveys with aircraft, helicopters, and they are much more generalized than our products. So you can see here the scale bar 300 kilometers, 200 kilometers, compared to the resolution of our products, that is 10 kilometers. So what we did is we put together in a computer, in a machine learning, all the traits that we had about the pre-disturbance time of like the persistence of these changes and the magnitude of the changes. And we cluster all the possible responses that were found in our non-standard placement disturbances. So we found 7 different behaviors that we call exemplars of the non-standard placement disturbances. So the number 1, that would be the red, had a big and dramatic change that happened faster than any other disturbance. The number 5 and 6, the exemplars 5 and 6 that are blue and brown, will have a slower and more gradual changes compared to the 1. Or we have exemplars like the 3, that is the olive color, that are much longer and much subtle than any other through time. So we accounted for the amount that each of these different traits of these different exemplars occupy in Canada's forest. So we saw that overall the exemplars 7, 4, and 6, so would be this purple, this brown, and the green, are the most common in Canada, and the exemplar 1 and 3 are actually the most uncommon. And we were able to map these exemplars across Canada. So we saw that the exemplar 6 was very common in northern forested areas. So we can see that actually one characteristic of the exemplar 6 is a low pre-disturbance spectral response. We could see like the 7 was distributed across all Canada, but not in the taiga shield and boreal shield ecozones. The exemplar 2 was more common on the east, and the exemplar 1 and 3, like they never dominated any of the 50 kilometer grids that we use to analyze this data. So what we also saw the distribution of these exemplars within the information we had, the field collected information we had about mountain pine beetle, drought, and spruce bootworm. And we compared that information with the overall baseline for all Canada. So we saw that for the mountain pine beetle and for the spruce bootworm, like the exemplar 7 was more common. So I kept here the graph of how the exemplars were more common than the Canada baseline or in drought areas. We could see also like the spruce bootworm in the exemplar 2, was more common than for the other cases analyzed. And we can see like for the water stress, the exemplar 6 is actually the most common in this kind of characteristics. We did this analysis. I will go a bit faster here. We did this analysis also, but by forest type. So coniferous this is the proportion of forest in Canada. Coniferous is the most common, and as expected, they had the higher amount of non-stand replacement disturbances. And then this is followed actually by well-land treed areas, and broadleaf and mixedwood have a much lower amount of non-stand replacement disturbances based on the representation. And we were able also to map where is the normalized abundance, so what proportion of each ecozone was affected by each of the different exemplars we used. So we can see like Mountain Cordillera in BC was actually the ecozone that had the largest abundance of non-stand replacement disturbances. And then we have information about the forest structure. We were able to see what was the impact of these non-stand replacement disturbances in the different forest structures. So we can see like most of the exemplars that we track, they resulted in a loss of cover at the stand level of the canopy cover. But at the same time, like the majority of our exemplars actually resulted in an increase of the height, which is indicated by elevation P95, on the height of the stands. And we could be, as we could expect, like the stand that had the largest pre-disturbance values experiences the greatest losses on biomass or canopy cover. And in contrast, the areas that had the lowest pre-disturbance value had a lower decrease or even an increase on the values of biomass following the disturbance. And as a conclusion, I would like to just repeat some remarks here. The first one is like, it's obvious that remote sensing technology, together with the open access to the data and the use of high performance computing systems, provide like really great opportunities for monitoring forest ecosystems, not only the land cover, but also changes and forest structure. There are some challenges, and there are some important challenges on the characterization of the non-stand replacement disturbances. Like the first one is like the same agent might have different representations and have different impacts in different geographic areas. And the second is like different agents might have similar spectral manifestations. So this is something that we need to keep in mind. We approach this non-stand replacement disturbance analysis using exemplars that are based on the analysis of the time series to identify how and where these changes occur. And we believe that it's important to develop a nomenclature about what are the characteristics that remote sensing can provide for the analysis of the non-standard present disturbances. So we have information about the persistence, the spectral persistence, the spectral response before, the spectral response after, the magnitude of the change. So those are all new tools that enable us to understand the impacts of the non-standard present disturbances and to track the change of those impacts through time. A quick reminder, some of the data that we have produced is openly available in the National Forest Inventory System. So you can access to this website and you can navigate through it, or if you actually want to work with it in your local computer, you can download it with the links we provide. And that's all what I have to say. Thank you very much.